Hey guys, today we are going to solve a numerical based on stoichiometry. The hourly energy requirement of an astronaut can be satisfied by the energy released when 34 grams of sucrose are burnt in his body. How many grams of oxygen would be needed to be carried in the space capsule to meet his requirement for one day? First of all, we'll focus on sucrose and oxygen. We need to know the molecular formula of sucrose, which is C12H22O11. Now, when this is burnt in the body, it reacts with oxygen so that we have the reaction of respiration to give us carbon dioxide and water vapors along with the energy. The next thing we need to do is balance the reaction. Carbon 12 atoms, so we'll put a 12 on the product side. Next is hydrogen 22 atoms, so we'll put a 11 before water molecule. And this is going to affect the oxygen atom. So oxygen is 12 to 24 and 11 oxygen atoms. Already here we are having 11. So the next thing we need to do is put a 12 for balancing. So 12 twos are 24 atoms. So right now the reaction is being balanced. So we can just write down the stoichiometric relationship between sucrose and oxygen gas. In the question, they have provided us with 34 grams, that is mass of sucrose, and we have to find out the mass of oxygen. That means we are going to deal with the mass-mass relationship. So the first thing that should be coming to our mind is the standard mass, which is molar mass of sucrose. So the molar mass of sucrose will be equal to 12 atoms of carbon multiplied by 12, that is the atomic mass of carbon, plus 22 atoms of hydrogen multiplied by 1, which is the atomic mass of hydrogen, plus 11 atoms of oxygen multiplied by 16, that is the atomic mass of oxygen. Get it as 342 gram mole inverse. The next we need to find out is the molar mass of oxygen gas, which is 2 atoms of oxygen multiplied by 16, that is the atomic mass of oxygen. So we get it as 32 gram mole inverse. Now we can write down the relationship between the mass, standard mass I mean to say, of sucrose, that is 342 grams of sucrose will be equal to, or we can say corresponds to, 32 grams of oxygen gas. But as you can see in the reaction, we are having 12 moles of oxygen. So since the stoichiometric coefficient is 12, what we are going to do is 12 multiplied by 32 grams of oxygen. Now we will once again come back to the question and observe that 34 grams of sucrose is for the hourly energy requirement. That means I can write here 34 grams of sucrose is for 1 hour. But they are asking for oxygen, which is required for 1 day. So 1 day is 24 hours. So for 24 hours, how much will be the sucrose? So mass of sucrose will be equal to 34 multiplied by 24, which comes out to be 816 grams. So that we can find out the mass of oxygen for a day. Let's come back to the stoichiometric relationship. 342 grams of sucrose. So below that we will write down 816 grams of sucrose, which is the requirement for a day. This will correspond to a question mark, that is mass of oxygen required for 1 day. So now it's simple. Cross multiply. Mass of oxygen would be 816 into 12 into 32 divided by 342. This will come out to be, let's use log over here, anti-log of the characteristic of 816 will be 2, for 12 it will be 1, and for 32 it's again going to be 1. Now the log of 816 is 9117, that for 12 is 0792, and that for 32 is 5051. Since there is multiplication sign, we will add this. Here we get 0, 6, 9, 4, and here we get a 5. Now let's subtract 342's log, that is 2.5340. So we get it as 0, 2, 6, 9, and here we'll get a 2. Now the antilog for this will be 9162, putting a decimal directly after one digit, into 10 raised to 2. This is the power, 10 raised to 2. So we get it as 916.2 grams. So the daily requirement of oxygen for the astronaut to be carried in the space capsule is going to be 916.2 grams. Thank you.